Hello everyone, welcome to a new lecture of our Processing in Memory course. Today we are going to talk about benchmarking and workload suitability on a real-world processing in memory architecture. Remember that in our previous lecture, we talked about programming a general-purpose processing in memory architecture, and in particular, we focused on the ADMEM-based PIM systems. An ADMEM-based PIM system, as you may remember, is composed by a host CPU that is connected to several DRAM DIMMs that work as the main memory and also some DIMMs of PIM-enabled memory. On each PIM-enabled DIMM, there are several chips, and inside each of the chips, there are several DRAM banks called NRAM, and connected to them, there is a in-order pipeline called DRAM processing unit or DPU. Remember that the ADMEM-based PIM system follows the accelerator model, where the host processor needs to explicitly copy data from the main memory to the PIM-enabled memory, and then launch the kernel execution on the memory side by using a specific command. After that, the processors in DRAM perform operations, execute a kernel, and at the same time, the CPU can check continuously when the kernel on the memory side has finished. After that, the memory banks on the PIM-enabled memory become again accessible to the host processor, and the host processor can retrieve the results and move them, copy them to the main memory. Remember as well that we talk about some programming examples, and the first one that we covered was the vector addition. In vector addition, what we do is equally partitioning the input and the output arrays and distributed them over the available DPUs in the system. And inside each of the DPUs, we also distribute the workload among the available software threads or tasklets. Remember that a key reference for learning how to program general purpose PIM architecture as the ADMEM-based PIM system is the user manual or programming guide that you can find in the ADMEM SDK documentation. Remember as well that we gave like 4 general programming recommendations, the first one being executing on the DRAM processing units or DPUs portions of parallel code that are as long as possible. Second one is split the workload into independent data blocks which the DPUs operate on independently. And third, use as many working DPUs in the system as possible in order to maximize the parallelism. And the fourth, launch at least 11 tasklets or software threads per DPU. We also talk about how to perform the data movement between the main memory and the PIM-enabled memory. Those are what we call the CPU to DPU and DPU to CPU data transfers. And we studied that there are 3 different ways of performing these transfers. The first one are the serial transfers, where we target a single DPU or a single NRAM bank. The second one are the parallel CPU, DPU, or DPU, CPU transfers, where we target multiple DPUs or multiple NRAM banks. And finally, the broadcast CPU DPU transfers, where by targeting multiple DPUs, we transfer a single buffer to all these DPUs. That's why it's called a broadcast operation. These CPU, DPU, and DPU, CPU data transfers are very important for us because we need to use them to enable inter-DPU communication, because of the reason that there is no direct communication channel between DPUs. We talk as well about some example communication patterns, for example, merging of partial results to obtain a final result. In this case, we only need to use DPU, CPU transfers, or the redistribution of intermediate results for further computation. In this case, we need to use DPU, CPU, and CPU, DPU data transfers. Today, we are going to continue talking about them. We will talk a little bit more about different workloads using these communication patterns, and we will see what are the implications of these communication patterns in the performance of the workloads on the ADMEM-based PIM system. We talk as well about another important workload, another key primitive for parallel programming is the parallel reduction. We discussed how to implement this parallel reduction by assigning parts of the input array to the different tasklets running on each DPU, obtaining some local sums, and finally performing a final reduction of the local sums by either using a single tasklet or single tasklet or using multiple tasklets in a tree-based reduction that can be implemented in different ways. We talk about barrier-based tree-based reduction and also handshake-based tree-based reduction. With all this knowledge about how to program a general purpose processing in memory system, we work as well on identifying different benchmarks that can be different workloads that can be suitable for general purpose processing in memory systems. And this is the reason why we created the PrIM benchmark suite with the goal of creating a common set of workloads that can be used to evaluate PIM architectures, and in particular the ABMEM PIM architecture, compare software improvements and compilers, compare future PIM architectures and hardware. And in order to decide what workloads to turn into a PIM or PrIM benchmarks, we use two key selection criteria. The first one, we selected workloads from different application domains, and also we selected workloads that are memory-bound on conventional processor-centric architectures. In total, in PrIM benchmarks, there are 14 different workloads and 16 different benchmarks, because for two of the workloads, we have two different versions. These are the application domains and the whole list of PrIM benchmarks in its current shape. We have dense and sparse linear algebra benchmarks, databases, data analytics, graph processing, neural networks, etc. All these workloads can be considered memory-bound in processor-centric systems, and in particular, you can see in this slide the Roofline model obtained with Intel Advisor on an Intel Xeon CPU, and as you can see, all the 14 workloads fall in the memory-bound area of the Roofline. So they are expected to be memory-bound in processor-centric architectures, and due to that, they are expected, or hopefully they will be suitable for processing in memory systems. PrIM benchmarks are also diverse. They are diverse in terms of memory access patterns because they have sequential, strided, and random access patterns. They are diverse in terms of operations and data types, and also in terms of communication and synchronization, intra-DPU and inter-DPU. Regarding the inter-DPU communication, we find some PrIM benchmarks that use inter-DPU communication for result merging. In this case, remember that we only need to use DPU to CPU transfers. A good example of this is a histogram generation where we obtain partial histograms in each of the DPUs, and at the end of the execution, after the kernel terminates, we have to move the partial histograms to the host processor for the host processor to perform final merging of this subhistogram. And also another inter-DPU communication pattern is the redistribution of intermediate results that we can find typically in graph processing workloads, for example, where we have multiple iterations, and in each iteration we generate a frontier and we have to redistribute the frontier between iterations. Other workloads that also need this sort of redistribution of intermediate results are, for example, Needleman-Wunsch. In Needleman-Wunsch, we are creating a two-dimensional matrix, and we go anti-diagonal by anti-diagonal. After having computed one anti-diagonal, we return the control to the host processor in order for the host processor to launch the next kernel that will execute the or compute the next anti-diagonal. In this case, for this redistribution of intermediate results, we have to use both DPU, CPU, and CPU, DPU data transfers. So let's keep learning about this general purpose processing in memory system. And in order to do so, and in order to evaluate this processing in memory system for different types of workloads, for these different PrIM benchmarks, we are going to do a thorough experimental study that is also going to reveal some interesting characteristics or important characteristics that will make real-world workloads suitable or not for this general purpose processing in memory system, this ABMEM architecture. So let's go with the benchmark evaluation. First of all, let's talk about our evaluation methodology. We evaluate the 16 PrIM benchmarks on two ABMEM-based PIM systems of different size. The first one is a large PIM system with 2,556 DPUs. The second one is a smaller one with only 640 DPUs. On these systems, we perform strong and weak scaling experiments. In particular, we are going to show you results on the larger system for those who need a refresher on what's a strong and weak scaling. Strong scaling refers to how the execution time of a program solving a particular problem varies with the number of processors for a fixed problem size. While weak scaling refers to how the execution time of a program solving a particular problem varies with the number of processors for a fixed size problem size per processor. We perform strong scaling experiments on one DPU, changing the number of tasklets per DPU. We also perform strong and weak scaling experiments on one rank. Remember that one rank has 64 DPUs, and we also perform strong scaling experiments on up to 32 ranks. After that, we compare as well the performance and the energy consumption of the admin-based PIM systems to state-of-the-art CPUs and GPUs, in particular an Intel Xeon and an NVIDIA Titan 5. In this slide, you can see the different data sets that we use for strong and weak scaling experiments. These are the data sets for one DPU and one rank for 32 ranks. This is the data set for weak scaling, and these are the MRAM, WRAM transfer sizes that we have used in our experiments, and here they are for reproducibility of our results. In our publicly available repository, you can find all codes, scripts, and data sets that we have used in our evaluation. Let's start with the strong scaling experiments on one DPU. In these strong scaling experiments on one DPU, what we do is we change the number of tasklets or software threads on the DPU from 1 to 16. And in the experimental results in the plots, we show the breakdown of the execution time for the DPU kernel time. So it's the execution time of the kernel running inside the DPU, the inter-DPU communication, the time for inter-DPU communication via the host CPU, the CPU to DPU data transfers, the DPU to CPU data transfers, and finally, we also show the speed up of the DPU kernel over the performance of the DPU kernel for a single tasklet. So let's start with some observations here. One thing that we can observe is that for the majority of the kernels, the best performing number of tasklets is 16. We observe linear speedups of something between 1.5 and 2.0 times higher speedup when we increase or when we double the number of tasklets from 1 to 8, and then a slightly lower speedup, something between 1.2 and 1.5 times when we increase the number of tasklets from 8 to 16. The reason for that is that the pipeline throughput, as you may remember from the corresponding lecture, saturates at 11 tasklets. So one key observation is that a number of tasklets greater than 11 is a good choice for most real-world workloads that we tested, in particular for 16 kernels out of 19 kernels that we have in the 16 PrIM benchmarks. And the reason is that 11 or more tasklets fully utilize the DPU pipeline. Another observation is that there are several workloads that don't use intra-DPU synchronization primitives, while in others, there is intra-DPU synchronization, but this is pretty lightweight. As a result, we see that the workloads scale nicely, these workloads scale nicely, and we obtain the highest performance with 16 tasklets. However, there are 3 workloads that use mutexes, and this causes contention when accessing shared data structures, and in some way limits the scalability of these workloads. For example, for one of the versions of the histogram calculation, we can observe that the lowest DPU execution time or the lowest DPU kernel time occurs for only 8 tasklets. So that's the case where we obtain the highest speed up. The reason for that is that this version of the histogram uses mutexes, and every time that a tasklet wants to update one bin in the histogram, needs to lock the access to the histogram, and it will only be this tasklet, the one that will be updating the histogram, while the others have to wait before accessing the critical section to update the histogram. So intensive use of intra-DPU synchronization across tasklets using mutexes, barriers, handshakes, etc. may limit scalability, and sometimes causing that the best performing number of tasklets is lower than 11. There is another observation. This scan SSA, in particular, the add kernel, is not compute intensive. In this case, the performance saturates with less than 11 tasklets. But the reason for that is not related to the use of synchronization primitives, because this add kernel of scan SSA doesn't use any intra-DPU synchronization primitives. The reason is that this is it's not a compute-intensive workload. It's more like a memory-intensive workload. And in this case, what happens is that the latency of accesses to MRAM, the data movement between MRAM and WRAM, this latency is hiding the latency in the pipeline. So even though most of the workloads are in the compute bound region of the DPUs, and that's why we expect that most of the workloads saturate at 11 or more tasklets, there are some workloads, in particular in the PrIM benchmark suite, we have one kernel in scan SSA, and also the BES binary search benchmark. They are memory bound on the DPUs, and they are so. In this case, the memory access latency dominates over the pipeline latency. Okay, so some more observations. The amount of time spent on CPU, DPU, and DPU, CPU transfers is low compared to the time spent on the DPU execution for most of the workloads. It's only in this transposition benchmark where the CPU DPU transfer is actually performing one step of the matrix transposition, and that forces us to use small transfers of only 8 elements. And what this causes is that we are not fully exploiting the CPU DPU bandwidth, and that's why we see this large CPU DPU communication time. But in general, transferring large data chunks from to the host CPU is preferred for input data and output results due to higher sustained CPU, DPU, and DPU, CPU bandwidths, as we could see in our previous lecture for the micro-benchmark experiments that we showed for the communication between the host and the PIM-enabled memory, between CPU and DPUs. Now let's move to the strong scaling experiments on one rank. In this case, we set the number of tasklets to the best performing one per DPU, as we have obtained in the previous experiments on a single DPU, and we changed the number of DPUs from 1 to 64 inside the same rank. The breakdown of execution time shows the DPU kernel time, the inter-DPU communication time via the host CPU, the CPU DPU transfer time, the DPU CPU transfer time, and the speed up all over one DPU. So let's take a closer look at the results. One first thing that we see that for most of the PrIM benchmark, we see that the strong scaling experiments on one rank scale linearly with the number of DPUs. However, scaling is sublinear for BFS and NW. In BFS, the problem is that different DPUs suffer from load imbalance due to the irregular graph topology. So the amount of computation that is assigned to each DPU is not exactly the same, and this load imbalance limits the scalability. While in Needleman-Wunsch, the thing is that even though we might be using the maximum number of DPUs, in the end, in each iteration of the algorithm, we just need to use as many DPUs as really needed to compute one of the anti-diagonals of the 2D matrix. And because the size of the anti-diagonals is not regular, in some cases, we would be using more DPUs for the larger diagonals, while for the shorter diagonals, we don't use all DPUs. So that's the reason why in the overall execution of the algorithm, we don't see linear scaling. One more observation is that these benchmarks, VA, GenV, SPMV, VS, TS, and transpose do not need inter-DPU synchronization, while in others, they need inter-DPU synchronization, but 64 DPUs still obtain the best overall performance. However, there are these three workloads, BFS, MLP, and Needleman Bunch, that require heavy inter-DPU synchronization, involving DPU, CPU, and CPU, DPU transfers. And that's why we see that for these three workloads with the red apron, the inter-DPU communication time is clearly noticeable. Another interesting observation is that for all these benchmarks, we can use parallel transfers, and the CPU, DPU, and DPU, CPU transfer times decrease as we increase the number of DPUs because we are using parallel transfers. In the case of BS and NW, we use parallel transfers, but the CPU, DPU, and DPU, CPU data transfers, the data transfer time do not seem to be significantly reduced. There are reasons for that. In the case of BS, we are transferring a complete array to all DPUs. So even though we are using more DPUs, we are not reducing the amount of data that we have to transfer per DPU. While in NW, it happens something related to what we just described about the scalability of the DPU kernel. The problem in NW is that we are not using all DPUs in all iterations, so we are not parallelizing the transfers over all DPUs, but only over those that we are really using for the calculation of each anti-diagonal. Then we see that in SPMB, Select, Unique, and BFS, they cannot use parallel transfers because the transfer size per DPU is not fixed. So one programming recommendation here is parallel CPU, DPU, and DPU, CPU transfers inside a rank of DPUs are recommended for real-world workloads when the transferred buffers are all of the same size. Remember that if we don't have buffers to transfer from or to the different DPUs of the same size, we'll have to use serial transfers. Let's move now to the experiments on 32 ranks, strong scaling experiments on 32 ranks. Again, we set the number of tasklets per DPU to the best performing one, and we change the number of DPUs from 256 to 2048 DPUs. Here we show the breakdown of execution time, and in particular, we show the DPU kernel time and the inter-DPU communication time. We do not include in these plots the CPU, DPU, and DPU, CPU transfer times. And finally, we also show the speed up over 256 DPUs. Let's take a closer look at the results. So as we can see, for all these benchmarks, we see that the performance scales linearly with the number of DPUs. However, for these three workloads, SPMB, BFS, and NW, we don't see linear scaling due to load imbalance. So load imbalance across DPUs ensures linear reduction of the execution time spent on the DPUs for a given problem size when all available DPUs are used, as we observed in these strong scaling experiments. Another observation is that these benchmarks only need to merge partial results. So the overhead of merging partial results from DPUs in the host CPU is tolerable across all PrIM benchmarks that needed it. As you can see, the inter-DPU communication time or inter-DPU time is quite negligible for these workloads. However, for other workloads, they have more complex communication patterns, and these more complex communication patterns involving both transfers from DPU to CPU and from CPU to DPU impose a significant overhead when we increase the number of DPUs that we are using in the system, and this limits the scalability to more DPUs. Finally, I'm going to also show you some results on weak scaling on a single rank. In this case, weak scaling, we have equally sized problems per DPUs, or we are increasing the size of the total problem as we increase the number of DPUs. And one key observation from these results is that equally sized problems assigned to different DPUs and little or no DPU synchronization lead to linear weak scaling of the execution time spent on the DPUs. That's something that we can observe, for example, here for BA, for GenV, even from SPMB, and many other of the PrIM benchmarks. We see linear scaling because essentially the kernel time remains flat as we increase the problem size and the number of DPUs. These are the results for BA, as we see flat DPU kernel time. However, we see that even though we are using parallel transfers in BA and in other benchmarks, the sustained bandwidth of the parallel CPU, DPU, and DPU, CPU transfers inside a rank of DPUs increases, but it increases sublinearly with the number of DPUs. So let's continue with this experimental characterization. Now, comparison to CPU and GPU. Let's talk about the evaluation methodology in these experiments. We compare both APMEM-based PIM systems to a state-of-the-art CPU and GPU, an Intel Xeon and an NVIDIA Titan V GPU. We use state-of-the-art CPU and GPU counterparts of the PrIM benchmarks that you can also find in our repository. And we use in these experiments the largest data set that we can fit in the GPU memory. We show the overall execution time, including the DPU kernel time and the inter-DPU communication time. So that's what you're going to see in the next plot. In this plot, we show in the y-axis the speed up over the CPU, and then as you can see, we are going to see some bars for the different PrIM benchmarks. Some of these PrIM benchmarks are identified as more suitable for the PIM system. Others are less suitable for the PIM system, and here you can see this geomean of the first, the second group, and the overall geomean for all 16 workloads. So one first observation is that both PIM systems outperform the CPU for all benchmarks except SPMB, BFS, and Middleman-Bush. And both APMEM-based PIM systems are respectively 93 times and 27.9 times faster than the CPU for 13 of the PrIM benchmarks. So all PrIM benchmarks except SPMB, BFS, and NW. Another observation is that the larger APMEM-based PIM system outperforms the GPU for 10 of the 16 PrIM benchmarks with an average of 2.54 times. And the performance of the smaller APMEM-based PIM system is within 65% the performance of the GPU for the same 10 PrIM benchmarks. Key observation here is that the APMEM-based PIM system can outperform state-of-the-art GPUs on workloads with 3 characteristics that are the key characteristics of these 10 workloads where the larger PIM system outperforms the state-of-the-art GPU. And these 3 characteristics are: first, streaming memory access patterns; second, no or little inter-DPU synchronization; and third, no or little use of integer multiplication, integer division, or floating point operations. Remember that these complex operations are not natively supported by the APMEM ISA. So they are emulated, and that causes a significant reduction of the compute throughput. So workloads with these 3 key characteristics are potentially suitable to the APMEM PIM architecture. In terms of energy, we also clustered the results in a similar way for more PIM suitable workloads, less PIM suitable workloads, and here you can see the different geomeans. We could only run energy experiments on the smaller APMEM-based PIM system. The energy measurement wasn't available, wasn't enabled in the larger PIM system, but in the smaller PIM system, we already observed some interesting energy results. On average, this 640 DPU system consumes 1.64 less energy than the CPU for all 16 PrIM benchmarks. And actually for 12 of the PrIM benchmarks, the PIM system provides energy savings of 5.23 times over the CPU. So key observation here is that the AppMem-based PIM system provides large energy savings over the state-of-the-art CPU due to the higher performance and thus the lower static energy and the less data movement between memory and processors. Second observation here is that the AppMem-based PIM system provides energy savings over state-of-the-art CPU, GPU on workloads where it outperforms the CPU or the GPU. And this is because the source of both performance improvement and energy savings is the same. The significant reduction in data movement between the memory and the processor cores, which the AppMem-based PIM system can provide for PIM-suitable workloads. In order to finish this lecture, let me give you some key takeaways of our analysis. The first key takeaway was already covered in a previous lecture when we discussed the micro-benchmarking of the DPUs and the AppMem PIM architecture. We observed that the AppMem PIM architecture, the DPUs have a memory bound region and a compute bound region, and the throughput saturation point, that is the frontier between the memory bound region and the compute bound region, is pretty low for all data types and operations. So the key takeaway was that the AppMem PIM architecture is fundamentally compute bound. So we are going to expect that most of the workloads that we port to this new architecture will fall in the compute bound region of these of the DPUs. So as a result, we also expect that the most suitable workloads for the architecture are those that are clearly memory bound in processor-centric systems. The second key takeaway, as we have discussed in this lecture, is that the most well-suited workloads for the AppMem PIM architecture use no arithmetic operations or use only simple operations, right? Such as bitwise operations or integer addition and subtraction. And they essentially avoid complex operations that are emulated, like integer multiplication and division and floating point operations. The third key takeaway is that the most well-suited workloads for the AppMem PIM architecture require little or no communication across DPUs, so no inter-DPU communication. And finally, our last key takeaway, the AppMem-based PIM system outperforms state-of-the-art CPUs in terms of performance and energy efficiency on most of PrIM benchmarks. They outperform state-of-the-art GPUs on a majority of PrIM benchmarks, and we think that the outlook is even more positive for future PIM systems, keeping into account that this AppMem-based PIM architecture is only 3 years old, while GPUs and CPUs have been optimized in terms of software, hardware, and architecture over decades. And the AppMem-based PIM systems are more energy efficient than state-of-the-art CPUs and GPUs on workloads that they provide performance improvements over CPUs and GPUs. You can find the summary of these key takeaways in our short paper that was presented at the CAD workshop in 2021, and you can find all the results, all the workloads, key observations, programming recommendations, etc., in the longer version of our work that you can find in archive. Remember as well that all our workloads, data sets, benchmarks, and micro-benchmarks are publicly available in our repository. In upcoming lectures, we will continue talking about more real-world processing in memory architectures. We will also talk about processing using memory architectures and prototypes, and also a few more important topics on processing in memory. So I hope you enjoyed the lecture, found it useful, and please don't hesitate to reach out to me whenever you need to clarify any questions related to this course. And thank you very much for your attention.